Okay, hello. Uh, what we're going to do today is we're going to talk about the Woolhouse approximation in actuarial science. So, and we'll want to see some of the background. So, way I will describe this will be numerical approximation, uh, which is behind the Woolhouse approximation. And so, and we're gonna just worry about the three term. So, and here's how I'm going to start. I'm going to start by saying a few words about approximating certain kind of improper interval. So for us, what we're really going to do is we're going to look at a formula to approximate the improper interval of f of t dt, and we will assume that f is positive, that f is decreasing, strictly decreasing, that f goes to 0 as t goes to infinity in a monotone fashion. And we'll also assume that the derivative goes to 0 as t goes to infinity. Now, given that f is going to be a multiple of a survival function in actuarial science, well, no one lives forever. So these are all very reasonable assumptions for the functions that we use in actuarial science. And let's first of all, let's just focus on this type of interval here. Now, the very first thing, if you notice, the red is supposed to be the graph of the function, and the black things that I've just drawn are the trapezoidal approximations for f. So, and just as a reminder, the integral of a function you can think of as the area underneath the curve, bounded by the curve and the x-axis. And the trapezoidal approximation means that we approximate the graph of this function by piecewise linear intervals and take the areas of the trapezoids instead. So let's just work on that, and let's just keep that thing in mind. So first of all, let's look at a finite interval. And what we're going to do is we will decompose our x-axis into segments of length h. And the very first thing we will do is we will first approximate this interval here. So from 0, and we're going to go n of these intervals length h, and we wish to approximate this. So now the very first thing we want to do is just take a look at the calculus 2 trapezoidal rule. Now the calculus 2 trapezoidal rule, basically what you do is you approximate the area under this curve by an area under the approximating trapezoid. This here has height f sub 0. In this case, this will be height f sub h. The illustration shows h equal 1, but there's nothing really special about 1 here, just some positive value. And as you recall from elementary geometry, the area of each trapezoid is going to be the average height. So it would be this. Average the height multiplied by the base. So this is a base, and this is the average height. And we do this again. And now we're starting at FH, 2H, average height, and so on until we get to the final term. That would be F of, since we go out to n intervals, it's going to be n minus 1 times h plus f of nh over 2. So this is a trapezoid approximation. Now, what we can do here is notice that these two terms belong to two of the trapezoids. These two terms belong to two trapezoids, as will this. The only ones that don't are the first term, the first term of the first term, and this one here. So what I can do is I can write this as, I am going to go ahead and multiply this. Well, I'll just write it like this. So we have h f0 over 2 plus, now I'm going to have all these h's here. Notice this appears twice, and it's division by 2, so those cancel. Again, there's a 2 down here, but that appears in two of these. So we go all the way down to the end. And then we get the very last one that only appears in one of the trapezoids. So what we can do, and we're looking ahead to the actuarial science application of this, I'm going to go ahead and add an extra one of these. So I'm going to, just because I can, I want to add one. I'm going to add one of these. And then I'm also going to subtract one. Oh, there's an H here. And so now look what I get. What we get out of this is we get now the sum H, then we can start at 0. And go all the way out to NH. But then we have to subtract off these. So it's going to be minus H over 2, the function evaluated at 0, plus the function evaluated in H. Okay? So this is going to be this is a first order, or this is a trapezoid approximation for this interval here. Now what we're going to do is, now if we wanted only the first two-term Woolhouse, we wouldn't have to go any further. We could just work with this approximation. But what we'll note, that if we took a limit as n goes to infinity, that's going to be approximately what we get as a limit as n goes to infinity. And then we have this. Well, we know by our assumptions, that's going to turn out to be a 0. And assuming that this is a convergent integral, and it better be since these are the things we work with, you get this approximation using just the trapezoid rule. Now notice this is going to be the sum from, let's say, I equals 0 to infinity of f of I h minus h over 2 function evaluated at 0, and that goes to 0. And again, this would be enough to get the two-term Woolhouse if we wanted to stop there. This is enough to use to get the two-term Woolhouse approximation. But we want to go to the three-term, so we aren't going to stop there. So we want to go ahead and add on correction terms. So let's just go ahead and select this and do something with it. Oops. So let's just give ourselves a little bit more room here. Now, what we're going to do to get the next order approximation, and I'd like to give a shout out to Dr. Nighttime. I will put that in the comments. But if you notice, because this is a convex function or concave up, notice that the trapezoidal rule is an over approximation. So in order to do that, I like to add a correction term, and the correction term would be the difference. Will be the difference between an approximating function which I'm going to call G, and the trapezoid approximation. And what we're going to do is we're going to use the cubic spline. So we use a cubic spline on each segment. And we're going to use what's known as a clamp spline, if you know what a spline is. Now, basically what that means is we're going to use the spline, but it's going to be on the spline will be the difference between this function and this. So it's a spline on the difference. So you can think of the function we're going to actually be splining is this little segment rotated so that this black part of the trapezoid is on the x-axis, right? So what we end up doing is that we have the knot right here, the knot at h and the knot at 0. So the function we're going to approximate, we're going to have g of 0 equaling 0. We're going to have g of h equaling 0 because there's no difference between the function we're approximating and the trapezoidal segment, top part of the trapezoid, right? So we have that. We also are going to specify derivative conditions. So the derivative condition at the first will be the derivative, since the difference of the function is going to be this difference here, and I'm going to move in this direction here. Actually, I'm going to move, I'm going to take this away from that. That'll be negative. So that's going to be f prime of 0 minus k, where k is the slope of this line. G prime of h will be f prime of h minus that slope k. Now, you notice the k is going to vary from segment to segment, just like the values of the functions do. Now, what I'm going to do is I'm going to denote this difference here by y not prime, and I'm going to denote this difference by y1 prime. Now, the spline that we're going to use, the spline's going to have equation g of, I guess, t will be a t cubed plus b t squared plus c t plus d. Now, this condition here, g of 0 equaling 0, means d is 0. That was easy. G h equaling 0 means ah cubed plus bh squared plus ch is 0. And so let's solve for c. C is going to be important. So this means that c is equal to minus ah squared minus bh, assuming you can handle those two things. But this value of c is also going to be important, because if we use this condition for the derivative, right? So let's calculate the derivative of g. We see that g prime of 0 is also c. So what we get out of this is y prime 0. So let's, oh, I just realized I wrote this upside down. Put my prime as a subscript. Hopefully that doesn't shake your confidence in me too much, but there we go. Right, that's C. Now, the interesting thing here is G prime of H is 3AH squared plus 2BH plus C, but C is just Y0 prime, right? And remember, G prime of H, we said, is going to be Y1 prime. So let's, just for grins, let's compute Y0 prime minus Y1 prime, and we get minus 3AH squared minus 2BH. Now, let's save this for just a little bit. There's a reason we're doing that. We will come back to this. We're not going to actually solve directly for B and H because we don't have to. We don't have to solve for B and H. What we can do is now let's integrate our function without the D between 0 and H, because remember, we're going to, instead of integrating this function, we're going to integrate the difference between this function and the trapezoid, because it's a correction term and we're just going to add it in. So integrating from 0 to h of g of t, that's going to be the integral from 0 to h of a t cubed plus b t squared plus c t dt. And this is just a basic calculus 1 integral, no problems here. It's ah to the 4th over 4 plus bh cubed over 3 plus ch squared over 2. And I did the integral pretty quickly. Now, let's get a common denominator. Let's factor out an h squared. And so we get this. C over 2. But remember what C was. C, remember, as minus AH squared minus BH. And so let's just substitute what we have for C. Minus AH squared minus BH. Okay? And we just substituted that. And there's a reason for this, because now we have AH squared over 4 minus AH squared over 2 plus BH over 3 minus BH over 2. And getting a common denominator, this, well, we don't need a common denominator yet. This is minus AH squared over 4. And if you use a denominator of 6 here, so this is 2 minus 3, so it's minus B H over 6, right? So that's 2 6 minus 3 6 is minus 1 6. Now let's do the common denominator of 12. So it's minus 3AH squared minus 2BH over 12. But let's just take a look at what that was. Minus 3AH squared minus 2BH. And that's what we have here. So if you zoned out, that's okay, because that is precisely y sub naught prime minus y1 prime. But notice what those were. Those were the derivative at 0 minus k and derivative of at h minus k, and the k's cancel. So this turns out to be 1/12 the derivative at 0 minus the derivative at h, which is what we wanted. So notice what we did is we did the spline on the difference between this trapezoid approximation and approximating this difference here. And notice we can do this for all h. So this gives us a refined approximation. And notice, and I should say note, and I'll paper this over here, but notice if we go as limit as nh goes to infinity of this derivative, that was assumed to be 0 by assumption also. So we are now ready to refine our approximation, right? So we're now ready to refine this. So what we get now is 0 to infinity of f of t dt is approximately, then we get this infinite sum, h, infinite sum, I equals 0 to infinity, f of ih. That's going to be our annuity and our mth annuity due, that is, because it does start at 0. Then we get our trapezoid right here, minus h over 2, f of 0. And then we add to that, um, oh, yes, yes, yes. And I just made this little faux pas here. When I was doing all this, h squared minus h, I got a little carried away when we divided through by the h's here. That I forgot to carry this h squared here. I'll just put this in. Okay. So, yeah, better fix that. Um, better do that here. That's important. And so it's going to be h squared over 12 times f prime of 0. Okay. So we do have, now this part right here, this is going to be the first two terms of the Euler-Maclaurin approximation, or I should say 3. Now you can carry this out for all the terms you want, but assuming you have, the function is say C infinity or something like that. But we are now ready to come up with a Woolhouse. Now remember we did this for H. So now, getting back to our Woolhouse, let's now put this integral in terms of something we understand. So where we're now going to integrate from 0 to infinity is this, which you might recognize is the continuous annuity life x. Okay? Now for h equal 1, now we're going to use h equal 1. This term right here becomes annuity due, because it does start at 0, life hx, minus 1/2, function evaluated at 0, plus 1 over 12, first derivative evaluated at 0. Now we will fix this up at the end, where f is, I should say what f is. We'll fix it up in just a second. So that's what your f is. It's just a little easier to leave that as f. But we can also we can now take a step h equal 1 over m. So this is also the nth annuity due life hx. This part is now, remember, it's 1 over 2m because you have an h here, plus 1 over 12m squared. All right? So now let's copy this into a new slide. Whoop, I don't want to do that. There we go. Now let's solve for what we want to approximate. And what we really wanted to do with this is that we wanted to approximate this term here. Well, these are equal. So now what I can do is I could say this, the nth, is going to equal this. Well, now I'm going to add this to both sides. So it's going to be minus 1/2. Let's see here. let's just do it this way. Add 1 over 2m here minus 1/2. And then we do the same thing here. So now this is I'm going to go ahead and subtract this. That's 1/12 minus 1 over 12m squared. And there is a plus error, which I'm not going to worry about. I told you this is not a numerical analysis. And this is, of course, is approximate. Now let's just do some terms here. So getting the old common denominator, it's 1 minus m over 2m. Notice that's negative, so we'll fix that. And then this one here, this is going to be m squared minus 1 over 12m squared. We're almost at the Woolhouse, but not quite. We do have to figure out what the heck this is. So what the heck is this? Now remember, your F was e to the minus force of interest t times this. So now the derivative with respect to t, because remember x is not varying, but t is going to be the derivative of the first using the product rule. Now I know you know the product rule, plus this times this derivative here. Now, in case you want a little help with that, you might know that immediately. Remember, the force of mortality at x plus t is minus the derivative. It's really the proportional derivative. So solving, that's going to be your derivative here. So your f prime of 0 will be minus force of interest plus, that's going to be a 1. And this will be mu minus, because left off my sign here. That's important. You add a 0 for t, but the survival to times 0 is 1. So f prime of 0 is just going to be minus a force of interest, minus a force of interest plus a force of mortality at time x. Okay? So now we get to the official three-term Woolhouse. And that is going to be this right here. And then we have the what I call the trapezoidal term. So I'm going to subtract m minus 1 over 2m. And notice this is the same factor right here that you use in accelerated claims when you're talking about insurance. And f sub 0 is 1 minus m squared minus 1 over 12m squared. And the minus comes from the this part right here. Force of interest plus force of mortality at time x. So there you go. That's a derivation of the three-term Woolhouse. Thanks for watching.